Welcome to your personalized deep dive. Today, we're going to be taking you down the rabbit hole of Einstein's relativity.
Oh, boy.
Using excerpts from Relativity, a very short introduction by Russell Stannard.
Okay.
Now, I know what you're thinking.
I'm not sure I do.
You're curious about Einstein's mind-bending theories, but maybe you're thinking, do I need a physics degree to understand this stuff? Well, guess what? Nope, not at all. That's where we come in.
All right.
We're going to break down both special and general relativity, focusing on the most intriguing concepts and their implications for the real world, you know?
Real world implications.
Exactly. So get ready for some seriously mind-blowing stuff.
Yeah, hold on tight because some of this is going to get really weird.
Okay, so before we jump into the really mind-blowing stuff,
Yeah.
let's just start with what we all think we know about, time, space, and motion.
Okay.
Kind of the common sense stuff, right?
Right. We tend to assume that time ticks at the same rate for everyone, everywhere, right? A meter is always a meter, regardless of how fast you're moving, right? And motion? Well, that's just about how fast something is going compared to something else.
Pretty straightforward, right?
Simple.
Right, totally. But here's the thing. Einstein's theories challenge these seemingly obvious ideas.
You do.
And here's the cool part. We can actually follow his thought process using logic and everyday observations. So no need to get bogged down in, complicated equations or anything like that.
Yeah, not yet at least.
Not yet, exactly. So to kick things off, one of Einstein's fundamental building blocks is this idea called the principle of relativity. Have you heard of this?
Oh, yeah.
It states that the laws of physics are the same for all observers who are moving at a constant speed and direction.
Right.
In physics speak, we call these inertial observers.
Inertial observers, yeah.
So that means that someone chilling here on Earth and someone cruising through space at a steady speed would experience the same laws of physics, right?
That's exactly right.
Okay, wild.
Now, one of these laws of physics, we can use it to calculate the speed of light in a vacuum.
Okay.
Here's the ticker. This speed is constant for all inertial observers.
Okay.
Doesn't matter how fast the source of light is moving or how fast you're moving when you measure it. It's always the same, 299,792,458 kilometers per second.
Wow, okay.
It's pretty mind-boggling.
Hold on. So if I'm chasing a beam of light at, say, half the speed of light,
Okay.
it's still going to be moving away from me at the full speed of light.
That's right.
That doesn't seem right.
It's true, though.
Really?
It's been proven experimentally. Take the experiment at CERN with these subatomic particles called neutral pions. These pions were traveling at nearly the speed of light, and they emitted light pulses as they decayed.
Okay.
And guess what?
Yeah.
Those pulses, they still traveled at the speed of light, even though they came from this super fast source.
Wow.
Crazy, huh?
Yeah, okay, that's pretty wild. And then this whole idea was further solidified by another famous experiment, the Michelson-Morley experiment, right?
Right. So scientists initially thought that light needed a medium to travel through. Like how sound waves travel through the air.
Right.
They called this hypothetical medium the ether.
Is it ether? Okay.
But the Michelson-Morley experiment, they tried to detect this ether, and it failed. It showed that light travels at a constant speed, regardless of the Earth's motion, suggesting there's no ether at all.
So we've got this principle of relativity, where the laws of physics are the same for all inertial observers.
Okay.
And we've got this fact that the speed of light is constant for all observers.
Yes.
But those two ideas, they seem kind of like they clash, don't they?
They do seem to clash, yeah.
How can they both be true?
That's the question Einstein was grappling with. And his answer. It revolutionized our understanding of space and time. He realized that for both of these ideas to be true, our intuitive notions of space and time, they had to be wrong.
Wow, are you serious? You're telling me that our everyday understanding of time and space, that's all just totally off?
That's right.
That's a pretty huge deal.
It is a huge deal. And it leads us into this mind-bending world of special relativity, which focuses on how constant speed affects space and time.
Okay.
Einstein, he tackled this in 1905, and it led to some incredible concepts. You ready to dive in?
Absolutely, hit me with it.
Okay, let's start with time dilation.
Time dilation, okay.
The idea that time isn't absolute, it's relative to an observer's motion.
Wait, time dilation, does that mean time can actually slow down?
That's exactly what it means.
I'm having flashbacks to high school physics class.
That's okay, we'll take it slow. So, picture an astronaut in a spaceship, traveling at a significant fraction of the speed of light, with a clock on board. And back on Earth, we have an identical clock.
Okay.
What we would observe is that the astronaut's clock is running slower than ours.
Seriously. So time literally flows at a different rate for the astronaut compared to us here on Earth. That's like, I'm trying to wrap my head around that.
Yeah, it's a mind bender, for
Yeah.
sure. It all comes down to that constant speed of light we talked about. If it's truly the same for both the astronaut and us, even though they're moving incredibly fast relative to us, something has to give. And that something is time.
Okay, so time, isn't this like universal, unchanging thing that we always thought it was? It's like flexible and it's relative to your motion.
That's right.
That's wild. But hold on a second. How would the astronaut perceive our time? Would they see our clocks here on Earth running faster?
Now, here's where it gets even weirder. Remember the principle of relativity.
Mm-hmm.
Motion is relative.
Right.
So if we see the astronaut's clock running slow, they'll also see our clock running slow.
Wait a minute. How can both clocks be slower than the other one? It's like a time-bending paradox.
It does seem paradoxical, right?
Yeah.
But remember, we're not comparing these clocks side by side.
Right.
The astronaut is far away, and we rely on signals, like light, to compare the times.
Right.
And because it takes time for those signals to travel, the calculations, they get tricky.
Okay.
It's not as simple as just looking at two clocks next to each other.
So you're saying like the whole idea of comparing clocks in different frames of reference gets really complicated because the speed of light is involved.
Exactly. And that's just the beginning.
Okay.
Next, we need to tackle how this all affects our perception of distance. Are you ready for more?
Bring it on. This is fascinating, even if it is making my brain hurt a little.
That's a good sign. It means we're on the right track. So are you ready to delve a little bit deeper into this rabbit hole?
Oh yeah, lead the way. We were just talking about how time is relative, but what about distance? Does relativity mess with that too?
Oh, absolutely. It wouldn't be relativity if it didn't, right? Let's stick with our astronaut, now on a mission to a distant planet.
Okay.
We've already established their time is dilated, meaning it's running slower from our perspective here on Earth.
Right.
But wouldn't they also calculate a shorter distance traveled because of that slower time?
Yeah, I guess so.
And wouldn't that violate the principle of relativity?
It would seem like it. How can both the principle of relativity and time dilation be true if the astronaut can figure out that they're the one moving?
Well, that's the thing. Distance is relative too, just like time.
What? So you're telling me that the spaceship would literally look shorter to us on Earth?
Exactly. And it's not an optical illusion. It's a real effect of space-time itself. Of course, the astronaut wouldn't feel squashed because everything inside the spaceship, including their own body, would contract along with it.
Okay, I think I'm starting to see a pattern here. Time dilates, length contracts. It's like the universe is constantly playing tricks on us.
The universe loves to keep us on our toes, that's for sure.
But didn't you also mention something about simultaneity being affected too? Like how our idea of now gets all messed up by relativity?
You've got a great memory. You see, we tend to think that events happening at the same time for one person happen at the same time for everyone else, right?
Right, that seems logical.
But Einstein showed us that this common sense idea, it isn't always true.
Okay, give me an example.
All right, let's go back to our astronaut in the spaceship. This time, imagine they have two light sources, one at the front and one at the back.
Okay.
They send out light pulses simultaneously, one towards the front of the ship, the other towards the back.
Okay, like a cosmic light show.
Exactly.
Yeah.
Now, from the astronaut's perspective, it seems obvious that those pulses hit the front and back walls at the same time,
Yeah.
right? Because they travel the same distance at the same speed.
Yeah, that makes perfect sense. But I have a feeling that's not what happens from our perspective here on Earth.
You got it. A mission controller watching from Earth would actually see the pulse traveling towards the rear of the ship hit first.
Wait, seriously, how is that even possible?
Well, remember, the spaceship is moving from the mission controller's perspective.
Right.
So the back wall is moving towards its light pulse, while the front wall is moving away from its pulse.
Okay.
And since the speed of light is constant, the rear pulse has a shorter distance to cover, and thus arrives first.
So what you're saying is what seems simultaneous to the astronaut isn't simultaneous to someone back on Earth. Does that mean cause and effect can get messed up? Like, is it possible to see the effect of something before its cause?
That's a great question, and luckily the answer is no. The idea of cause and effect, or causality, still holds strong.
Okay, good.
Einstein's theory ensured that events can only influence each other within a specific region of space-time, called their light cone.
Light cone.
Yeah, picture a cone on a diagram with its tip at a particular event. The cone represents all the possible paths light could take from that event, spreading out in space and time.
Okay.
Events inside the cone are causally connected. They can influence each other. But events outside the cone are too far away in space and time to have any causal relationship.
So those light cones help us see which events can potentially affect each other and which ones are totally independent.
Exactly. It highlights this really mind-boggling implication of four-dimensional space-time.
Yeah.
The idea of a block universe.
A block universe. All right, now you've really got me intrigued.
The block universe suggests that space-time isn't this dynamic, flowing thing that we perceive it to be. It might actually be a static block, with all events past, present, and future existing simultaneously within it.
Hold on, are you saying everything that's ever happened or ever will happen is already laid out like a movie on a DVD?
It's a wild idea, right?
Yeah.
But the block universe, it's incredibly controversial. Many physicists, and probably you too, struggle with the idea that the past and future exist on the same level as the present moment.
Yeah, it's hard to let go of this idea of time flowing, you know? It's such an intuitive feeling.
I get it. But before we dismiss the block universe completely, consider this. If only the present exists, how do we even define what events are happening now when simultaneity itself is relative?
That's a good point. It's like trying to nail down jelly. The minute you think you've got it, it slips away.
That's the challenge of relativity. It forces us to rethink our most basic assumptions about the universe. But even if we don't fully embrace the block universe, it raises fascinating questions.
Yeah.
If the past, present, and future all exist together, what does that mean for the nature of time itself? What is this flow that we experience?
Okay, now my head really hurts, but in a good way.
Ready to keep going? Because all of this is still just special relativity. We've got a whole other theory to explore.
Let's do it. Bring on general relativity.
All right, but first I need to ask you something.
Yeah.
What's your experience with the concept of gravity? Like, what comes to mind when you think about it?
Well, I mean, my common sense understanding is that gravity is like a force of attraction between objects with mass. The bigger the object, the stronger the gravitational pull.
That's the classical view, the one Newton gave us. But you probably guessed it. Einstein had other ideas. General relativity gives us a whole new understanding of gravity. And it starts with something called the equivalence principle.
Okay, the equivalence principle. Lay it on me.
It's pretty simple, but it's really profound. It says that you can't distinguish between the effects of gravity and the effects of acceleration. They're equivalent.
Hold on a second. Are you saying gravity and acceleration are the same thing?
Not exactly the same thing, but their effects are indistinguishable.
Okay, I need an example.
Okay, picture yourself in an elevator. No windows, just you and your imagination. You're just standing there, and suddenly you feel this pull downwards, like gravity's getting stronger. What do you think is happening?
Well, I'd probably assume the elevator was at rest here on Earth, and I'm just feeling normal gravity pulling me down.
That's one possibility.
Yeah.
But here's another. What if the elevator is actually out in deep space, far from any planets or stars, and it's accelerating upwards at a constant rate?
Yeah. Inside the elevator, I wouldn't be able to tell the difference between those two scenarios, would I?
Exactly. That's the equivalence principle in action. You can't tell the difference between being at rest in a gravitational field and accelerating upwards in space.
Okay, now my mind is really starting to bend, but this raises a question. Does that mean you could create artificial gravity using acceleration?
You got it. Think about astronauts in a spaceship continuously accelerating. They'd feel this pull toward the back of the ship, just like gravity, and they wouldn't be able to tell the difference between that and standing on a planet.
So science fiction just became science fact. But this equivalence principle, it's more than just a cool thought experiment, right? It actually has some real-world consequences.
Oh, absolutely. Remember how we talked about special relativity and how time is relative? Well, general relativity takes that idea and runs with it. It shows us that gravity also affects time.
Wait, what? You're telling me gravity can mess with time too? Tell me more.
Okay, let's picture that spaceship again, but this time it's accelerating upwards. And there's a light source at the back of the ship that's sending out pulses toward a target at the front. What do you think happens to those light pulses as the ship accelerates?
Well, the target at the front is moving away from the light source faster and faster as the ship accelerates. So I guess the pulses would arrive less frequently, kind of like a stretched out wave.
You nailed it. That's exactly what happens. It's similar to the Doppler effect with sound waves, where the pitch changes depending on whether the source is moving towards you or away from you.
Right.
But in this case, it's light waves that are being stretched out,
Okay.
shifting their frequency towards the red end of the spectrum. We call this redshift.
Okay, I'm following so far. Acceleration causes redshift. But how does gravity fit into all of this? I thought we were talking about general relativity.
That's where that equivalence principle comes back into play.
Yeah.
Remember, we can't distinguish between acceleration and gravity.
Right.
So if acceleration causes redshift, then gravity must also cause redshift.
Whoa. Are you saying that clocks in stronger gravitational fields actually run slower? Like time itself is being affected by gravity?
That's exactly right. It's called gravitational redshift. The stronger the gravitational field, the slower time runs. And this isn't just a theory, it's been confirmed by experiments.
Okay, my mind is officially blown.
Yeah.
How do scientists even measure something like gravitational redshift?
They do it by observing light coming from distant objects with really strong gravitational fields, like white dwarf stars or neutron stars. These objects, they have immense gravity, and the light they emit is redshifted compared to light from objects with weaker gravitational fields. There have even been experiments here on Earth that measure this effect.
Really?
Yeah, like the Pound-Rebka experiment. They measured this tiny, tiny redshift of light traveling up a tower right here on Earth.
So gravity really does slow down time, and this isn't just some theoretical curiosity, it has actual practical implications too, right? Like for GPS satellites and stuff.
Exactly. If we didn't account for the effects of both special and general relativity, GPS systems wouldn't be nearly as accurate.
Wow, it's amazing how these mind-bending concepts from relativity actually play a role in our everyday technology.
Right, and that's not all. This connection between gravity and time, it leads to an even more mind-bending prediction. Gravity can actually bend light.
Hold on, gravity can bend light. That's insane. How does that work?
Let's go back to our spaceship one more time. Imagine a beam of light shining across the spaceship, perpendicular to the direction of acceleration. From an outside observer's perspective, what do you think that light beam would look like? What path would it take?
Well, if the ship is accelerating upwards, I guess the light beam would appear to curve downward.
Exactly. Now apply the equivalence principle. Remember, no difference between acceleration and gravity. What can we conclude about how gravity affects light?
Well, if acceleration bends light, then gravity must bend light too. I'm starting to get the hang of this relativity thing.
You got it. And you know what? That's exactly what scientists observed. It was one of the first major confirmations of Einstein's theory.
Wait, there was an experiment that actually measured this light bending effect.
There was. It's a classic experiment in the history of science. In 1919, Arthur Eddington led this expedition to observe a solar eclipse. And during the eclipse, they were able to measure the positions of stars that appeared close to the sun's edge.
Okay.
And guess what? Their positions were shifted slightly compared to their normal positions.
Yeah.
Exactly as Einstein's theory predicted.
Wow, so it's like the sun is acting like a giant lens, bending the light from those distant stars.
But wait a minute, didn't Newton predict that light would bend in a gravitational field too?
He did, yeah.
So what was the big deal about Einstein's prediction?
Well, Newton's prediction for how much light would bend was off by a factor of 2, compared to what Einstein's theory predicted. So Einstein was right, and Newton's classical physics was wrong. Another win for relativity. But this whole thing still seems kind of strange to me. We usually think of gravity as this force between objects with mass. How can it affect something like light, which has no mass?
That's an excellent question, and it leads to one of the most profound insights of general relativity. Gravity isn't a force at all.
Hold on, you're saying gravity isn't a force. If it's not a force, what is it?
Einstein reimagined gravity as a curvature of space-time itself.
Whoa, okay, you officially lost me. Curvature of space-time. What does that even mean?
Okay, think about it this way. Imagine a bowling ball placed on a trampoline.
Okay.
It creates a dip in the fabric, right?
Right.
Now, imagine rolling a marble across the trampoline. What happens to the marble's path?
Well, it would curve inwards towards the bowling ball following the dip in the trampoline fabric.
Exactly. In Einstein's theory, massive objects like stars and planets, they warp space-time around them, just like the bowling ball on the trampoline. And other objects, including light, simply follow the curves in space-time. That's what we experience as gravity.
So it's not that the Earth is pulling on me with a gravitational force. It's more like the Earth has warped space-time around it, and I'm just following those curves, like the marble on the trampoline.
That's the general idea. It's a completely different way to think about gravity. And it explains why light is simply following the curvature of space-time caused by massive objects.
Okay, I think I'm starting to visualize it. But this concept of curved space, it's still kind of mind-blowing. I mean, it's not like space is a physical thing that can actually be bent, right?
Right. Visualizing curved space, or more accurately, curved space-time, is incredibly tricky. We tend to think of space as this empty void, just nothingness. But physicists, we view space as this dynamic medium, kind of like a fabric that can be stretched and warped by the presence of matter and energy.
Okay, so space is more than just nothingness. But how do we know that it's actually curved?
You don't have to see the curves directly. Think about the Earth. It's a sphere, but if you were a tiny ant crawling on its surface, you wouldn't perceive the curvature. You'd think you were walking on a flat surface.
Right, but how would the ant know that the Earth was actually curved?
They could figure it out through geometric measurements. For instance, if they drew a triangle on the Earth's surface and measured its angles, they would find that those angles add up to more than 180 degrees. And that's different from what you'd expect on a flat surface, right? It's a clear indication of curvature.
Ah, I see. So we can use similar geometric measurements to detect the curvature of space-time caused by gravity.
Exactly. And experiments have done just that. They've confirmed that space-time is indeed curved. But this new picture of gravity as curved space-time, it's not just some abstract theory. It has some very real and fascinating consequences. For example, it explains the behavior of those ultimate cosmic enigmas. Black holes.
Black holes. Okay, now we're talking. Tell me everything.
Imagine a region of space-time where gravity is so strong that nothing, not even light, can escape. That's a black hole. They're formed when these incredibly massive stars collapse at the end of their lives, crushing all their matter into an unbelievably dense point.
So they're like cosmic vacuum cleaners sucking up everything in their path.
Not quite like a vacuum cleaner. It's more like falling into a bottomless pit. Once you cross the event horizon of a black hole, there's no going back.
Okay, what's the event horizon? Is that like the surface of the black hole?
It's more like the point of no return. It's the boundary beyond which the gravitational pull is so strong that not even light can escape. So anything that crosses that event horizon is lost forever to the outside universe.
That's both terrifying and fascinating. But what would actually happen if you fell into a black hole?
It wouldn't be a pleasant experience. As you approach the event horizon, you'd experience extreme tidal forces. You'd be stretched out in one direction and squeezed in the other. Physicists actually call this spaghettification.
Spaghettification. That sounds pretty uncomfortable. But wouldn't time also get totally warped near a black hole?
Absolutely. Remember that gravitational redshift we talked about? Well, near a black hole, the gravitational field is so intense that time practically stands still from the perspective of an outside observer.
So if you were watching someone fall into a black hole, they would just appear to freeze in time.
Pretty much. They would appear to slow down as they approach the event horizon and eventually just freeze in time before disappearing.
Wow, that's wild. But what about from the perspective of the person falling in?
That's the mind-bending part. As you fall into a black hole, you wouldn't actually notice anything strange about time. You'd cross the event horizon and just continue falling towards the center, experiencing time at a normal rate. At least until the spaghettification process kicks in.
So it's two completely different realities depending on your perspective. The observer sees time slowing to a crawl, but the person falling in doesn't notice anything unusual. Relativity is so bizarre.
It definitely challenges our intuition, but are all black holes the same?
Oh, that's a good question. I was just thinking about that.
The ones we've been discussing, formed from collapsing stars, we call those stellar black holes. They usually have a mass a few times greater than our sun.
Okay.
But they're also supermassive black holes.
Supermassive black holes? How massive are we talking?
We're talking millions or even billions of times the mass of our sun.
Whoa. Where do you even find something that massive?
Astronomers believe that supermassive black holes lurk at the centers of most galaxies, including our own Milky Way.
Wait, you're telling me there's a supermassive black hole right in the center of our galaxy?
That's the current thinking. And these supermassive black holes play a key role in the evolution and structure of galaxies.
That's incredible.
Black holes aren't the only mind-boggling prediction of general relativity, though. There's also the concept of gravitational waves.
Gravitational waves. Okay, those are definitely on my list of things I need to understand better.
They're ripples in the fabric of space-time itself, predicted by Einstein's theory.
Ripples in space-time. I'm having trouble even picturing that.
Think about it like this. Just as accelerating electric charges create electromagnetic waves, like light and radio waves, accelerating masses create gravitational waves.
So every time something massive accelerates, it sends out these ripples in space-time.
Exactly. But there's a catch. Gravitational waves are incredibly weak. Even for really massive objects like stars and planets, they produce incredibly faint ripples, which is why they're so difficult to detect.
Okay, I'm starting to see why these things are so hard to find. But how do scientists even try to detect them?
They use these incredibly sensitive instruments called interferometers. Basically, they use lasers to measure tiny, tiny changes in the distance between mirrors caused by the stretching and squeezing of space-time as a gravitational wave passes by.
And have they actually managed to detect these elusive waves?
They have. Back in 2015, the LIGO Observatory made history by directly detecting gravitational waves coming from the collision of two black holes billions of light years away.
Wow, after decades of searching, scientists finally confirmed Einstein's prediction. That must have been a huge moment.
It was a landmark discovery. Detecting gravitational waves opens up this whole new window into the universe. It allows us to study events that were previously invisible to us.
It's amazing how much Einstein predicted that we're only now able to confirm with our technology. Okay, we've talked about time dilation, curved space-time, black holes, gravitational waves. It's like we've gone on this incredible journey through all these implications of relativity. But there's one final frontier I want to explore. The universe itself.
Ah, yes, the grandest stage of all. And you guessed it, general relativity has a lot to say about the universe's structure and evolution. Ready to zoom out and consider the cosmos on the largest of scales?
Absolutely, let's do it. I'm ready for a truly cosmic perspective.
All right, so we know massive objects warp space-time locally. But what about the overall curvature of the universe itself? Like on the grandest scale, does it curve inwards like a sphere, outwards like a saddle, or is it flat?
That's a huge question. I mean, how do you even begin to measure the curvature of something as vast as the entire universe?
It's definitely a challenge. But scientists are clever, and they found some ingenious ways to do it. One key clue comes from the cosmic microwave background radiation, or CMB for short.
Oh, right. I've heard of the CMB. It's like a baby picture of the universe, right?
Exactly. And by studying tiny, tiny fluctuations in the CMB, scientists can infer the geometry of the universe.
And what have they found?
The universe appears to be remarkably flat, at least on the largest scales.
Flat. So the universe is like a giant sheet stretching out infinitely in all directions.
That's one way to think about it. Of course, there's still a chance the universe has a slight curvature that we haven't been able to detect yet, but for now we can treat it as flat.
Okay, so the universe is flat, but we also know it's expanding thanks to those observations by Edwin Hubble.
Right.
How does that fit into the picture?
The expansion of the universe, it's one of the most profound discoveries in cosmology. It means that the fabric of space itself is stretching, carrying galaxies along for the ride.
So galaxies aren't moving through space, it's more like space itself is expanding and pushing the galaxies further and further apart.
You got it. This expansion, it's happening everywhere, on all scales. Imagine baking a loaf of raisin bread.
Okay.
As the bread rises, the raisins, which represent the galaxies, they all get further and further apart.
That's a great analogy. But if the universe is expanding, what's the driving force behind it all?
That, my friend, is one of the biggest mysteries in cosmology. For a long time, scientists thought that the expansion must be slowing down because of gravity. You know, the attraction between all the matter and energy in the universe.
Right, you would think gravity would want to pull everything back together.
Exactly. But back in the late 1990s, astronomers made this shocking discovery. The expansion of the universe isn't slowing down at all, it's speeding up.
Wait, what? The expansion is accelerating. That's crazy. What could possibly be causing that?
Scientists believe there's this mysterious force, which they've dubbed dark energy.
Dark energy?
That's right. And it's responsible for this acceleration. It's like anti-gravity pushing everything apart.
Another cosmic mystery.
Indeed. We still don't know much about dark energy, but it seems to make up about 70% of the total energy density of the universe.
Wow. So we have dark matter and dark energy, these two invisible forces that we can't see, but that seem to be controlling how the universe behaves. It's like the universe is playing hide and seek with us.
You could say that, but even though we don't fully understand them, they're essential for explaining the universe as we observe it.
Okay.
So to recap, we have a flat, expanding universe dominated by dark matter and dark energy, and it's constantly accelerating outwards.
It's a lot to take in, that's for sure. But what does that mean for the fate of the universe? Does it just keep expanding forever, or what happens?
It's a question that has puzzled cosmologists for decades. The answer, as far as we know, it all depends on the balance between gravity and this mysterious dark energy. If gravity eventually wins out, the expansion might slow down and reverse, leading to what some call the Big Crunch, where the universe collapses back in on itself.
So like a cosmic rewind button, everything goes back to how it started.
That's the idea. But if dark energy continues to dominate, the expansion will just keep accelerating, leading to the big freeze scenario.
The big freeze. What happens in that scenario?
Well, in that scenario, the universe keeps expanding forever. It gets colder and darker as the galaxies move further and further apart. Eventually, stars burn out, black holes evaporate, and the universe becomes this vast, empty, and incredibly cold place.
Okay, that sounds a bit bleak.
It's not the most cheerful outcome, but it's one possibility.
Are there any other possibilities?
There are some more hypothetical scenarios, like the Big Rip.
The big rip.
Yeah, in this scenario, dark energy becomes so strong that it literally rips apart everything, from galaxies down to atoms. But for now, based on what we know, the Big Freeze, it seems like the most likely outcome.
So our flat, expanding universe, dominated by dark matter and dark energy, is probably headed for a rather chilly end. I don't know whether to be amazed or depressed.
It's definitely a lot to process. But it's incredible how much we've learned about the universe, thanks to Einstein's theories of relativity. From the tiniest subatomic particles to the largest cosmic structures.
It really is mind-boggling. We've come a long way since we started this deep dive, and I think I need a minute to just kind of digest it all. Okay, woo! I think I've finally caught my breath after that cosmic whirlwind tour of the universe.
Yeah, it's definitely a lot to take in. But isn't it incredible how much we've learned about the universe thanks to Einstein? From the tiniest particles to the largest cosmic structures, his theories of relativity have completely changed how we understand reality.
It's like we've been living in this black and white world, and then suddenly relativity comes along and reveals a whole spectrum of color. But, you know, it's not just the big abstract stuff that's mind-blowing. It's how relativity challenges our everyday assumptions about the world around us, you know?
Absolutely. Remember how we started this deep dive talking about all those common sense ideas about time, space, and motion? The things we thought we knew for sure?
Right, totally.
Relativity turns those ideas on their head.
Right, like the idea that time ticks by at the same rate for everyone everywhere.
Yeah.
We've learned that time is relative, influenced by motion and gravity. So your time isn't necessarily my time, especially if one of us is hanging out near a black hole or traveling at warp speed.
Exactly. And what about that notion that a meter is always a meter? Relativity shows us that's not quite true either. Thanks to length contraction, distances shrink in the direction of motion. The faster you go, the shorter things get. It's all a matter of perspective.
And then there's motion itself, that seemingly straightforward idea of how fast something is going relative to something else. Relativity threw a wrench in that one too, didn't it?
Definitely. Because the speed of light is constant for all inertial observers, we have to completely rethink how we add and subtract velocities, especially when we're dealing with speeds close to the speed of light. It's a whole new ballgame.
Okay, so those common sense ideas are officially out the window. But here's what I find truly amazing. Even though relativity seems so bizarre and counterintuitive, it's been confirmed by countless experiments and observations. It's not just some abstract mathematical theory, it's how the universe actually works.
That's right. Relativity has passed every test thrown at it, from the bending of starlight to the detection of gravitational waves. It's one of the most successful theories in all of science.
So for those of us who aren't physicists, what's the key takeaway from all of this? What does relativity really mean for us?
I think the biggest takeaway is that the universe is far stranger and more wonderful than we ever imagined. Our everyday experience of reality is just a tiny sliver of a much grander, more mind-boggling picture.
It's like we've been peeking through a keyhole and relativity has swung open the door to this whole universe of possibilities.
And that's the beauty of science, right? It constantly pushes us to expand our understanding of ourselves and the cosmos we inhabit. It invites us to question our assumptions, embrace the unknown, and just marvel at the elegance of the universe.
I couldn't have said it better myself. So for our listeners who want to dive even deeper down this relativity rabbit hole, what would you suggest as a next step?
Well, I highly recommend checking out the full version of the book we've been exploring today, Relativity, a very short introduction by Russell Stannard. It's a great starting point for anyone who wants a clear and engaging explanation of these concepts.
Excellent suggestion. And I just want to encourage everyone to keep questioning, keep exploring, and keep your minds open to the wonders of the universe. Who knows what other mind-blowing discoveries are out there waiting to be made?
Well, perhaps time isn't just a dimension, but a process unfolding within this block universe. Maybe what we perceive as the flow of time is an emergent property of something even deeper and more fundamental, something we haven't even begun to imagine.
That's a truly thought-provoking idea. It's like relativity has opened up this Pandora's box of questions about the nature of time and reality itself.
Exactly. And that's the beauty of science. It doesn't just give us answers, it sparks new questions.
Yeah.
It pushes us to keep exploring, to keep seeking a deeper understanding of the universe and our place within it.
Well said. And on that note, we'll leave you with that provocative thought to ponder. Thanks for joining us on this incredible journey into the world of relativity.
It's been a pleasure. Until next time, keep exploring.